Parametric equations and calculus. Well, very straight and direct, I think, in this section. We're given parametric equations, some function f, some function g in terms of t, that is x equal to f of t and y equal to g of t, are said to be our parametric equations. We want to be able to calculate the first derivative, the second derivative, and then also the arc length of a parametric system. We can calculate the slope and the concavity, the slope from the first derivative and the concavity from the second derivative. So when you evaluate the first derivative, you get the slope, and when you evaluate the second derivative, you get the concavity. So let's see. In terms of the first derivative, second derivative for parametric equation, dy over dx, the first derivative is dy over dt divided by dx over dt. If the parameter is theta, then you replace t with theta. The second derivative is kind of somewhat strange, but the second derivative is the first derivative that you have found earlier with respect to dt. So you take the derivative of the first derivative with respect to t, and that's divided by dx over dt. That's the second derivative, and that's all we basically deal with. If it's the third derivative, then you take the derivative of the previous one, the second derivative with respect to t, every time, always divided by dx over dt. The arc length is straightforward as well. The arc length from a while ago, from chapter 7, where we have the arc length of a function f, or here the function h becomes the integral based on the interval of the square root of 1 plus the derivative squared dx. But now we're given two functions, two parametric functions, so the deriving of the arc length based on the parametric form is the integral from a to b of the square root of f prime of t dt plus g prime of t to be squared dt. And so the f and the g are the parametric forms. And so just the formal statement, if c is a smooth curve given by the two equations, the two parametric equations, f and g, such that c does not intersect itself on the interval from a to b except possibly at the endpoints, then the arc length of c over the interval is given by this formula here. So let's go ahead and just put our knowledge to work. So here dy over dx is said to be first the dy over dt and that's over dx over dt. So the dy over dt is -6 and the dx over dt is 2t. So the answer would be -3 all over t. It's kind of hard trying to confine to those boxes. I do hate that, and I just should have put the result right there. But you get it. Secondly, find the first and second derivative, and then find the slope and the concavity if possible, given the parametric equations x and y. And so dy over dx is first the dy over dt, and that's divided by dx over dt. Well, dy over dt is 2, and then dx over dt is 4. So we just get a half. The second derivative with respect to x is the derivative with respect to t of the first derivative, and that's divided by dx over dt. Well, the derivative of 1/2 is 0, and that's divided by dx over dt, and we got 4. So this is 0. The slope here is 1/2. And then in terms of concavity, well, if the second derivative is 0, then this is a straight line or a straight plane, so there's none. No concavity. Let's move on to the next one. Again, the same repeat of questions, but here a different problem. So we find dy over dx. So this is d. So this is dy over dt, and this is divided by the dx over dt. Well, the dy over dt would give us 9, then divided by the derivative of x with respect to t. So we get 1/2 times t to the negative 1/2. It just gives us the 9 times the 2 is the 18 times the square root of t. So this is 18 times the square root of t. It asks for the slope if we evaluate t at 4. So we get 18 times the square root of 4. So here we get 36, and that's the slope. The second derivative is the derivative with respect to t of the first derivative. This is divided by dx over dt. Well, the first derivative gave us 18 times the square root of t. This is going to be 18 times 1/2 times t to the negative 1/2. And that's divided by the derivative of x with respect to t. And so that gives us 1/2 times t to the negative 1/2. And so here, most of these terms cancel out, just leaving an 18. 18 is positive, so the concavity is upward. Now the next problem, same question, find the first, second derivative, find the slope, find the concavity. They give you x and y, they give you a point here. We're dealing with an angle, theta. And this is taken right from online where they have the tutorial, and it's like 1 through 6. And you can look through how I worked that out there with respect to the computer. And that will be in Blackboard for you to see in terms of the PDF. Here's the problem here. Let's just work it out. So we find dy over dx. So this is dy d theta divided by dx with respect to theta. So the derivative of y with respect to theta is going to be 4 cosine theta. Then the derivative of x with respect to theta is negative 4 sine theta. So this gives us negative cotangent theta. So that's the first derivative. So now the slope is the negative cotangent theta, where theta, we evaluate that at power over 4. So this is negative cotangent of power over 4. Well, cotangent is 1 over tangent. The tangent of power over 4 is 1. So this is 1 divided by 1, and it's 1 times a negative, so we just get negative 1. Now what about the second derivative? So again, this is the first derivative with respect to the parameter, which is theta, of, take the derivative of the first derivative, divided by dx d theta. So we take the derivative here of the first derivative, that was the negative cotangent theta, and that's all over dx d theta, and that gave us negative 4 sine theta. So the derivative of the cotangent, well, let's see, the derivative of tangent is secant square theta, so the derivative of cotangent is negative secant square theta, so negative times negative is positive. So secant square theta, and we got that derivative, and that's negative 4 sine theta. Well, 1 over sine is cosecant, so this is negative 1/4 times cosecant to the third theta. Now we can find concavity. So concavity here is that second derivative evaluated here, where theta is power over 4. And it's just pi equal to power over 4. So negative 1 over 4 times the cosecant cube of pi over 4. And so we have negative 1 over 4. Cosecant is 1 over sine, and so sine of power over 4 is 1 over the square root of 2, so cosecant is the square root of 2. So this is the square root of 2 to the third power. So that gives us 2 times the square root of 2. So minus 2 times the square root of 2, and that's all over 4. So this is negative the square root of 2 all over 2. Okay. I don't think that there is anything else. Oh, in terms of the concavity, is negative, so it concaves downward. So negative second derivative, that means that here this curve concaves downward. Well, let's look at the arc length. Well, that's very straightforward and direct. So the arc length is the integral here from A to B. A is negative 1, B is 3 of the square root of basically x prime squared. So the derivative of x is going to give us the 9. So we square that. Plus the derivative of y is negative 6. We square that dt. So this is the square root of 81 plus 36. So that's the square root of 117 times the integral from negative 1 to 3 dt. Well, that just gives us the square root of 117 times t. T is evaluated from negative 1 to 3. Well, we just get 4 times the square root of 117. Well, I think that's it. So this section is very straightforward. Let's try to keep it simple. Have a good one. Thank you.